Right. In the last class, we studied green theorem. This is mainly about vector fields on a domain in a two-dimensional plane. Okay. So we are now going to study vector fields in three-dimensional space. Okay. Well, given vector field F, okay, so this is going to be three PQR, which is also written as PI, QJ, and RK, be a vector field in a region which is in R3, okay, three-dimensional space. Okay, this is just some region. Okay, now we're going to introduce a new concept. Okay, this vector field. Use this vector field, we can define another one, which is called the curl F. Right? A curl F is going to be another vector field, which is defined by the following formula. Okay, it is going to be partial derivative R with respect to Y minus partial derivative Q with respect to Z. That's the first component. The second component, partial derivative P with respect to Z, and partial derivative R with respect to X, that's the G. And the third one, partial derivative Q with respect to X, and partial derivative P with respect to Y, that's the K. Okay. Now, it's hard to memorize that, right? Oh, I don't know if next minute probably cannot write down this formula because there's partial derivative, right? So you can formally express in the following form. Okay, it's IGK here. This is a vectors. Okay, this is just determinant. Okay, partial derivative X, partial derivative with respect to Y, partial derivative with respect to Z, and then this P, Q, R. Okay, so that's much easier to memorize. Then if you want to find, you can expand this determinant along the first, we can expand this determinant along the first column, then you get above formula, okay? So we can expand the determinant along the first column, the first row, okay? Then you will get, you will get partial derivative Y with partial derivative with respect to Z, and the QR, this is I, right? Right, and remember, then it's minus because you have to change the sign. So you delete the first row and the second column. So what is left is partial derivative with respect to X, partial derivative with respect to Z, and P and R, okay? And that's a J. And then plus the last one is here, it's K. So here, partial derivative with respect to X, partial derivative with respect to Y, and P and Q. Right? Then there's still, partial derivative with respect to Y itself is not a number. It's just a formal notation. Then you still have to do the cross product and evaluate this determinant of 2 by 2 matrix. Okay. So then you will get, KSC, then do the cross product, right? Then this is going to be that, right? Okay, then you get that term minus then you get this term, right? Then you get the last Yeah. All right. So now you can write all the terms. Okay. So anyway, so a given vector field, you get another new vector field, and which is called the curl of F. Now there's a reason, yeah, we introduce this new vector field coming from the original vector field. Okay, let's look at a special case. Yeah, look at a vector field F, which is just P and Q on a domain and D in R2. Okay, so this one, this can be viewed as a vector field in three-dimensional space. Okay, it can be viewed as a vector field in the domain in the region R cross R, which is in R3. Okay, so you can still use the same F and PQ0. Okay, so P and Q are just function of X and Y. Okay, yeah, it's independently where P and the P X Y still, right? Q is still Q X and Y. Okay, depends on X only. The last component is 0. So then let's compute. Let's compute. Let's compute the curl of F. Okay. So what is the curl of F? According to the above formula, and I find out all the coefficient I, the coefficients of J, they're all 0. Okay, because when I is 0, so Q is independent of Z. So that's why partial derivative of Q with respect to Z is going to be 0. Okay. Okay. So what is left is only the last term. Okay, which is going to be partial derivative of Q with respect to X and partial derivative Y with partial derivative P with respect to Y and the K. And now you are familiar with this term, right? In Green theorem. Okay, great. So the dot product was the unit vector pointed to. So this is I, this is J, this is K, right? So this dot product gives you this. Okay, gives this. This is a function in the. This is a function in the Green theorem. So now you can see the domain D. Okay, and so the vector field was actually extended to the cylinder above this. With the cross section of D. Okay, so now we just back to this domain D in the XY plane. So according Green theorem, okay, according to Green theorem, the double integral, right? Okay, is going to be the line integral C, right? And this is a P dx plus Q dy. So we're going to write this formula in a slightly different way. And here, I'm going to just simply write curl of F dot K and dA. And this side, I'm going to write as just the vector field, okay, and T ds. Okay, so this is another version of the Green theorem. Okay, this is another version of the Green theorem. And this, if you parameterized the curve by R, okay, this is also written as C F dot dr. Okay, yeah, if the curve is parameterized by R. Okay, so this is a Green theorem, and okay, here F is just the original vector field in the xy plane. Okay. Now, if you want to study or generalize the green theorem to a vector field in three-dimensional space, then later on you're going to see that why we have to introduce a curl of a vector field. Okay, so this is a new version of the green theorem. Okay, without using P and Q. Okay. Right, and remember we have the theorem when a vector field is conservative, right? So recall that a definition. Recall that a vector field, right? A vector field is conservative. Doesn't matter in which dimension. Is conservative if f is greater than equal to f. So if f is a vector field in two-dimensional case, right? And that means if f is just p and the q, it's a vector field, right? Then f so let's see, this is the first case, not f, the first case. So f is a vector field plane. Then f is conservative if f is going to be gradient of f is just partial derivative of f with respect to x. Right? Yeah. And using that, you conclude that the necessary condition is going to be partial derivative q with respect to x is going to be the partial derivative p with respect to y. Okay, so that's what you get. The reason is that both are equal to this implies. Okay, if it's conservative, p and q must satisfy this condition. The reason is that this side is going to be partial derivative of f with respect to y, then with respect to x. And this is a partial derivative of f with respect to x and with respect to y. And we know that must be equal, okay? So that's why, the commutative, okay? So that's the reason you have the above equation. So now let's look at the two-dimensional case. F is going to be PQ, X, Y, Z, and the Q is X, Y, Z, and R, X, Y, Z. That depends on three variables, okay? So we assume that F is conservative, right? If F is going to be greater than F, which means right? So in other words, P is going to be f of x, Q is going to be f of y, and the I is going to be f sub z. Okay, sorry, f sub z. Okay, so now what you can get? Let's look at R. Okay, R in this case, this implies R y sub y is going to be f z y, right? F dy is fyz. So fyz is going to be qz. Okay, great. So you have this first identity. And then then P, Z, okay? P of Z, what is P? P is going to be Fx, xz. Then you exchange these two variables, Fzx, F sub Zx. F sub Z means the partial derivative of F with respect to Z. So it's going to be, yeah. So F sub Z is going to be R here, Rx. Great, right? Then the last one, Qx. What is Q? Q is Fy, F sub Y, then X, right? Then you exchange these two variables. So F sub, it's being P sub Y, okay? So you have those identities. Great. So simply you will get Ry minus Qz equals 0, right? Pz minus Rx equals 0, and Qx minus Py 0. Right. What this means? This really means the curve F is going to be 0. Why? Because this is Ry minus Qzi, right? And that's Pz minus Rxj. And here Qx minus Pyk. Okay, that's going to be 0. All right, so let's summarize what we discovered. That means by definition, okay, yeah, let me summarize, okay? If F, yeah, summary, right? If F is conservative, then curl of F is going to be 0, right? That's necessary condition, okay? Much easier to denote it, right? Instead of listing 3 equations. But, and yeah, so conservative means F is greater than or equal to F, right? Kept F. Then the curl is of F is going to be there. So if you have a vector field, the curl is, this is just necessary condition. Now, whether it's converse is true, remember in 2-dimension case, we talked about that, right? In 2-dimension case, if the domain is simply connected, it's simple, yeah, called simply connect, then you have the converse is also true, okay? If the partial derivatives, satisfy some equation, you can show that F is conservative. Right now, you only have one direction, okay, from here to here, okay? So this is a necessary condition, okay? Let's look at the example, okay? Let F to be xzi and xy, xyj, and plus yzk, okay? So this is a vector field defined on Rn. This is a vector field on R3, okay? 3-dimensional space. Let's calculate the curve. Okay, I already forgot the formulas, right? It's not easy to do that. So what I'm going to do is we use the formal definition. Okay, that's easy to memorize. And here xz, xy, and yz. Let's try to do the calculation. Okay, so that is going to be partial derivative okay, so here's the z and the x. No, the first one, you delete the first row and delete the first row and first column. So you have this xy, yz, that's I, minus the second column in the first row. Okay, and j and plus the reason I want to do that because I don't have the formula. I cannot memorize the formula. It's so complicated. It's harder to memorize it. Okay. So, but this is easy to memorize. Just only one single formula. Okay. Then you can have this logic here. Partial derivative x, partial derivative y. Partial derivative with respect to z. Okay. I, j, k. Okay. So now let's do the cross part, right? So the derivative here is going to be z. Okay. And that is going to be 0. So it's I minus here's 0 and minus x j plus it's y minus 0, it's k. So what we get here is going to be z I plus xj plus yk. Now which is not going to be 0, right? So the curl of the vector field is not going to be 0, then definitely we conclude that this is never being the this is the vector field f never be a gradient of some function. Okay, so f is not conservative. F is not conservative. Okay, so now let's look at next example. Consider f the following vector field. Okay, I'm going to express in this form: 2xy I plus xy x squared z squared, okay, plus 2yz k. Okay, let's look at this. And now, should I use a matrix again? Well, if you know the formula, okay, then I use the formula. Okay, this is a P, that's a Q, that is R. Okay. So the curl of F, okay, is going to be the partial derivative, right? Y minus QZ I. Yeah, let's write down all the terms. And this is a negative x minus pz. Okay, j and plus q sub x, p sub y, and k. Okay, so let's do the computation. So r sub y is going to be 2z, and the q sub z, the partial derivative q with respect to z, it's okay. Then r y, it's going to be 0. pz is also going to be 0. And the q sub x, q, where's the q? Okay, it has 2x, py, the derivative y with respect to, derivative p with respect to y, it's 2x. So they are all equal to 0. Now, we have a great chance to, so the question is f conservative? Is f conservative? Well, we have to find it, right? So then, because if f is conservative, the curl of f must be 0. So you have to find such f. So what they do is you just write down the 3 equations, right? So what is the first term? That's a p, right? Which is going to be 2xy, f sub y is q is going to be x squared plus z squared, and f sub z is going to be 2yz. Okay, well, that is r, and the 2yz. Okay, so let's try to, more likely it's going to get solutions. Okay, the only, we actually is on the, it's considered on the whole R2. Okay, R3. So R3 is nice. It's perfect domain. Okay. So is f conservative? It depends on the domain. Okay, if f is conservative on R3, let's figure out this. And we're trying to solve this as those equations. All right. How to solve it? Okay. Now, yeah, after finishing this problem, we're talking about the domain here. Okay. Right now, we just the function is perfect. The vector field defined on R3, so we don't worry about whether the regions connect or simply connect. Okay. So let's find out f. This is equation 1, equation 2, and the equation 3. I'm going to integrate the function on both sides with respect to x. Okay. So his side is f x y z, and then plus x squared y, and plus constant. The constant depends on y z. Okay. So this is by the first equation. Integrate the first equation. Then I have to plug into the second equation. Okay. Plug it into the second equation. Let's see what we can get. So partial derivative of f with respect to y, partial derivative of f with respect to y is going to be x squared plus cy. Now, which is going to be x squared plus z squared. Great. All right. So now, and the c sub y is going to be z squared. Okay. So let's solve for c. So you integrate both sides with respect to y. Okay. Then this side is cyz. Okay. The other side is going to be z squared y plus another constant, but depends on, it is constant with respect to y, but it still depends on z. Okay. So now you have the function, which is going to be x squared, x squared y plus c, right? C is going to be z squared y plus k. Okay. Then you have to plug into the last equation. The last equation is f sub z. When sub z is going to be, the first term is 0, second term is 2zy plus kz, okay? Which is going to be, where's my function? There, 2yz, okay? I know I have 2yz, okay? So that means p of z is little bit 0. That means k is indeed a constant. Okay, equals k, which is constant, independent of any variable. Okay, so finally, my solution is f is going to be x squared y plus z squared y and plus k, and it satisfies this equation. Okay, so f is conservative. Okay, f is conservative. Yeah, based on my calculation here, as long as the domain, when you integrate with respect to x or with respect to y, right? Now you have to be careful. So Yeah, the idea is if you have a domain, this is a domain, right, in three-dimensional space. Okay, let's call it A, right? So if the curve F, right, the question is whether you can find out the function. Yeah, suppose F is, the curve of F is 0. The question is whether you can find out little f, so that f is going to be the greater f, right? So the procedure is, the above procedure is just integrate, right? This is you fix a point, and this is an x, y, z. Okay. Now you have to, if you use an arbitrary curve path, then as long as this domain is going to be connected, that's enough, right? The problem is, how do you know the line integral be independent of the choice of a particular path from these 2 points? Okay. Yeah, you know, if the curve of f is 0, right? You want to find this little f, right? So if we are able to prove, under this condition, the line integrals, yeah. So you see, that's the way how to construct f, right? If f is greater than f, right? Okay, on this domain D, okay. Then for fixed point, then f, this f x y z, right, is going to be the line integral of f and dr, right? And t ds. Okay, got it? Yeah, because this can be the integral of from A to B, and that is going to be f, the derivative of f and gamma t, okay, dt. Okay, so yeah, so because it's a gradient, okay, you can go back to, because f is if f is a gradient of f, theta, okay, then and then for any parameterization of the curve, you have this. So that's what you can have. You can only that's why by the fundamental theorem of calculus, then the function little f is given by this formula. So as long as inside this domain, okay, if we can prove if the curve of f is 0, and this line integral is independent of the particular independent choice of particular curve, then f must be given by this formula. Okay, but we don't have the green theorem here, it's harder to say that. Okay, so if we know, okay, curve of f equals 0, and then the line integral is independent choice of particular curve c, and then we not only can prove f is conservative, we can also construct f by this integral formula. Now, what I did above is what I did above is actually is going to be special line integrals over using that. Okay, so so put this way, let me state the theorem. Okay, so we can at least I can show that. Yeah, it's a little bit difficult here. Okay, so if we are able to show for some domain D under the condition curve of f is 0, the line integral is independent of the choice of particular path between 2 points, then f must be conservative. Not only that, little f is going to be given by this formula. Okay, so here what I can claim. Okay, but I don't want to state a theorem. Okay, if okay, suppose curl of f is 0 on the domain D, and this line integral TDS, okay, is in, yeah, then the question, how do you verify this? Independent of curves from the 2 points, from P to Q in D for any pairs of numbers. Okay, suppose you have this property, then f is conservative. Okay, okay, namely f equals for some f, and moreover that f is constructed by the above formula. Okay, okay, f can be constructed by the above line integral. Okay. Anyway, what I can say here now, question is, what kind of a condition on the domain D guarantee this part is correct? Okay, and okay, we wish there's only one condition, the curl of f is 0. The next condition is on the shape of the D. So the theorem in the book says that, okay, I modify a little bit, let D be a rectangular domain in R3. Okay, it's called prism maybe. Okay, then and curl of f is 0. Okay, then f is conservative. Okay, and we prove that using just integrals, as I just showed to you. Okay, you just need to integrate on both sides, because this is what how do you do, right? If a p, how do you do that? F is going to be p q r, right? Right. Then and then you have this integral, right? Now this equation. Okay. Then you just integrate, because it's a box, so you can always fix a point. You can fix x0, y0, z0 in D, right? And then for an arbitrary point x, for any x, y, z in D, I just integrate. Right? This is the integral of f of x dx. Now the reason you can do the integration is because the line from this point to that point is going to be still stay inside the D. Okay, so so you can evaluate this integral and then you put a D here, integral, and this is a D P, right? Dx. Okay. Then after that, you can plug into second equation, blah blah blah. Then you can yeah, the partial derivative with respect to yeah, then you step by step, okay? Then this integrate the first equation, and you get this identity, okay? Then you do need the equation. The equations like a P. Yeah, so when you differentiate, if you put this into the second equation, then this will be the partial derivative of f with respect to y. Okay, then you end up with here the integral of the partial derivative p with respect to y. But that can be switched to you can switch to the q. Yeah, let me check. Yeah, so this is the idea. You see, then the partial derivative put into the second equation. Okay, then you will see that you can interchange that because x and y are independent variable. So you have get py dx, right? Then you get because p sub y is going to be qx. Okay. Yeah, q sub x. But now this time, this is derivative with respect to x, right? So you can have a q, okay, and integrate, right? So you have just f sub y, that's q. So it's meet to the second equation. Then you plug a constant, another constant k, c. Okay, the constant c depends on y and z. Okay, and then yeah, then it must satisfy the second equation. So the second part is 0. Then you're trying to solve for integrate, solve for y. Okay, so this is the idea, step by step, and then you eventually can get an f satisfy all the three equations. Okay, so this is just a rough idea. Now let's do another problem. Okay. Yeah, let's consider the vector field. Okay. Let me check. So that is going to be 2x y square. I'm going to modify this problem a little bit. So that's going to be y square z cubed, okay, and 2xy z cubed, and 3xy square z square. Okay. So this is a vector field defined on a whole I. Okay, is a vector field on the whole R3. Okay, so of course it's defined on the rectangular box. And I claim that curl F is going to be 0. Okay, it's easy to verify. Yeah, easy to be verified. Okay, easy to verify. It is easy to verify that. Okay. So I'm not going to check that just by direct computation. So therefore, so there is a function f defined on 3 such that, okay, such that f is gradient this. So I'm going to find such f. So f sub x is y squared z cubed. F sub y is 2xyz cubed. Fz is going to be 3xy squared z squared. All right. All right, so integrate the first equation with respect to x. I got f on this side, right? And yeah, this is x. So this is going to be y squared z cubed times x and plus constant yz. Now you can also yeah, let me put a little bit more details because we're talking about yeah, put more details integral from 0 to how about the x, okay, from 0 to x, more specific. Okay, so that's going to be x, okay, y is an arbitrary number, so z y z, right? So not much better, yeah, x, right? So actually when you move this to the right hand side, you get right. Then you plug into the second equation, so you will get f sub y when you differentiate with respect to the y variable, and they're going to be 2y z cubed x, and here this is going to be, yeah, here's x y z, and that will be the derivative. Okay. So according to the given information, you get 2xy z cubed, right? You can also submit it to plug into the third equation. Fzxy z is going to be when the differential is like 3y squared z squared and x. And this is supposed to be 3x squared yz squared. Okay. So after simplifying, you get right. So clearly the partial derivative with respect to y0, and that implies f0yz is going to be independent, okay, a constant independent of y and z. Okay, so we finally get the answer. That is going to be x y squared z cubed plus any constant k. Then my next topic, I'm going to I'm going to introduce so-called divergence. Given a vector field, F. Okay, that's a P, Q, R, 3 components. The divergence of F is defined by the following formula. It's going to be the sum of this partial derivative. Okay. Now, formally, you can write this notation. The dot product PQR. Okay. So you may call it this one. You may call it nabla. This is F. Okay. So this can be viewed as nabla dot F. Okay. That's just notation. Okay. It's the detailed formula is given by the above. The partial derivative P with respect to X plus partial derivative Q with respect to Y plus partial derivative R with respect to Z. Okay, sorry. All right. So why we want to do this? There's the motivation. One of the motivations to introduce divergence. Then, so given vector field, we get curl of the vector field. So this is another vector, right? Vector field. But not every vector field comes from the curl of another vector field. Okay, this is actually, yeah. So what I should say here is not every vector field is the curl of a vector field. What does that mean? Right, given vector field, arbitrary vector field, you get a curl of F, but those curl of F are special vector fields. Okay, so if you they're not an arbitrary vector field. That means an arbitrary vector field is not necessary to be the curl of the vector fields of some vector field. Okay, so so it looks like very arbitrary. Given vector field, I can get another vector field. Okay, but so actually they're not. They're very special. The curl of F is a special vector field. Okay, and how special it is. Okay, we can look at. Okay, so yeah, I want to prove that later. Okay, so let's look at the divergence. Okay, example. So if the vector field is going to be X, Y, Z, right? Then the divergence of the vector field is going to be it's going to be 3. So it's constant. It's a number. Divergence vector field is a number. Okay. Divergence of vector field is a number. And then here's another example. F. Okay. I'm using Y, Z, and here's X, Z, and X, Y. Okay. If we look at this vector field, the divergence of this vector field is going to be, okay, it's going to be, it's going to be 0. Right? It's going to be 0. All right, this is a good example, right? We, the next problem is for a vector field, we have the following theorem. Okay, if the vector field is going to be the curl of another vector field G, then the divergence of F must be 0. Wow. Okay. But this is a just necessary condition. It's not necessarily the sufficient. Okay. So we can let's prove. Let's prove it. Okay. So F is going to be the curl of G. Now let's assume that G is going to be PQR. Okay. So this is let's recall the formula. Yeah, it's easy to be forgotten. Okay. It's going to be R Y QZ PZ minus RX and QX minus PY. Okay, there's 3 components. All right, so you have this, right? Then let's look at the divergence. Divergence of F is RY QZ and partial derivative with respect to F plus PZ RX sub Y plus QX PY and Z. Okay, now let's write down the details. Y Z X Q Z X P Z Y X Y Q X Z and P Y Z. Huh. So P Y Z these 2 canceled out, and this also canceled out. Those 2 canceled out. Okay, so therefore it's going to be 0. Great. So that means if the vector field is the curl of another vector field, then the divergence it must be 0. But we know that there are vector fields is a curl divergence not equal to 0, right? So you conclude that F, right, X, Y, Z is not the curl of any vector field, because if it is the curl of some vector field, then the divergence is going to be 0. So it's not going to be 0, so it is not. And then you say, oh, how about the above one? You know, how about F, right? And Y, Z, and X. Let's see, what is our example here? Above, right? Y, Z, X, Y. And this one's divergence is going to be 0, right? So the question is F equal the curl of some for some G? It's hard to prove it. Okay, the reason is if G is going to be PQR, right? What do you have to do? You have to write down, you have to solve those equations. The curl of G, the first component is PY R sub Y minus QZ equals XYZ, right? Then the second equation, PZ and RX should be equal to XZ. And the QX minus PY, that's going to be XY. And this is a partial differential equations. It's much harder to solve. Maybe you're lucky, you can figure it out, right? Those are not easy. That's not easy question to find out. Okay. So we don't know. Yeah, it's harder to solve it. It's almost impossible to find it. Okay, so yeah, you can say I'm going to integrate, right? Because there are two functions involved. You know, you can integrate along. Yeah, you can integrate with respect to y variable. You get r, the first equation. But then how about how to deal with qz, right? So this is hard to solve it. So we don't know. Okay, we don't know. Okay, we don't know whether there's a solution or not. Okay, does it have a solution? Does this system of partial differential equations have a solution? It's hard to prove it. Okay. All right. So I want to I want to look at the following example. So if f is gradient of some f, okay? So that means it's going to be partial derivative of f with respect to x, partial derivative with respect to y, partial derivative of f with respect to z. So what is divergence of f? Okay. Well, by definition, the divergence of f is going to be the partial derivative of f with the first term. Then the partial derivative of second term with respect to y, you get double derivative, right? Okay. In mathematics, this is denoted by delta f, called the Laplacian of f. Okay. So this is an important problems in mathematics, whether or not there's a function satisfying the equation delta f equals 0. Okay, so this is a problem in mathematics. It's very important. So given a domain D, okay, so D in R3, okay, and trying to solve the equation we call lambda f constant, okay, and such that this around the boundary is going to be 0. Okay. Now, if such function exists, then the divergence of the gradient is going to be lambda f. Okay. So we are of course we are not going to start this type of equations. It's called usually it's written in the form like that, plus equals 0. Okay, lambda is positive number. Okay. Okay, there are some functions indeed satisfying the equations. Okay, one can construct. Okay, but so divergence of a vector field. Okay, so we have two types. Let's summarize. All right. So divergence of a vector field, if the vector field comes from the curl of another vector field, then this must be 0. Right? And the curl of the vector field. Yeah, the divergence of a vector field, if f is a curl of the vector field, then yeah. So let's see. Let me summarize it. Okay. So if this is true, then divergence of f is going to be 0, okay? And second, if f is a gradient of a little f, okay, then divergence of f is the Laplacian of f. Okay? It's not necessary to be 0 in general. Okay? And let's go back to the beginning. Okay, what is our motivation to introduce curl? Okay, the curl is 0 if the function is conservative. Yeah. So this is another question. Okay. So remember the curl of f. Yeah. So if let's go back here. Yeah. The third point is okay. If f is the gradient of little f, okay, that means conservative, then the curl of f is going to be 0. Okay, don't be confused. Okay, so yeah, the divergence is going to be the Laplacian for f. And but conversely, this is not true. Okay, so if the curl of f is 0, whether you can always find a little f, and this depends on the domain, the type of the domain. Okay, the type of domain is a rectangular box, yes, or the whole I R3. Okay, otherwise, yeah, otherwise it's they are this is not true. Okay, so we have a what kind of vector fields we're gonna have here? For the vector fields, either this can be the gradient of f, okay, and if it's gradient of f, then the curl of the vector field is 0. Okay, now this also can be the curl of another vector field. So confused, right? Then the divergence of it must be 0. Okay, but this is a necessary condition. So if divergence is not going to be 0, then this cannot be the curl of another vector field. So given the vector field, yeah, it's possible. A vector field could be possible. It's gradient of some function. It could be the curl of another vector field. Okay. Then if it's the curl of the vector field, then divergence must be 0. If the curl of if it's gradient of some function, then the curl of the vector field must be 0. All right, let's look at another example. So we have two types of special vector fields here. Okay, and let's do one more example. we consider f to be 2 x, y, z. Okay, let's just look at this again. Okay, let me explain to you. Okay, so this example, right? We see that curl of f is going to be 0. Okay, this is a 0. Okay, and in fact, f is the gradient of little f, which is going to be okay. So this is a f is conservative. Now, is f is yeah? Does f come from the curl of another vector field? Okay, then you have to look at the divergence. Okay, so look at divergence. Okay, it's going to be the partial derivative of this is going to be 3, okay, which is not going to be 0. So this is not going to be the curl of any vector field for any vector field G. Okay. But it's a very, I just showed to you, it's difficult to prove f is a curl of some vector field in case the divergence of f is 0, okay? But it is difficult to show that, maybe it's impossible to show that f is curl of G when the divergence of f is 0. Okay, in general, it's not necessary. It's not has to be true. Okay, so be careful about the relationship. Right now, if the curl of f is 0, more likely can find if the domain is nice, more likely can find the f little f, so that the capital F is going to be gradient. So this is almost equivalent, but here the divergence is 0 does not guarantee f is a curl of G, but f is curl of some vector field, then the divergence must be 0. Okay. Yeah, I'm going to show you example. Yeah, just a minute. Let me write down the function. So here's a vector field. Okay. F is going to be the first term is going to be 2y minus 2z. Okay. The second term is 2z minus 2x. The last term is 2x minus 2y. Okay, so it's kind of a symmetry, okay, type. So let's take a look at this example. I can leave with a constant, okay? So that's fine. Now, we check, okay? My question is whether this is conservative or whether, yeah, let's do lots of computation here. We can, my first question is, let's compute the curl of this, okay? Compute. For the vector field, you can compute those two things, right? Okay. So divergence of f, it's easy. This partial derivative of 2y minus 2z, whoops, that's going to be 0, right? And there's no y here. There's no z here. So that's going to be 0. So divergence is 0. Okay. How about the curl of this f? The curl of this f, okay? And this is a, if this is a p, this is a q, this is a r. Okay. So that's going to be ry, right? Let me write down qz I plus pz minus rxj plus qx minus pyj. Okay. So let's do the computation. R sub y is going to be negative 2 qz minus 2. All right, so that is a pz, p sub z negative 2, x q sub x negative 2, p sub y and it's negative 2. Okay, wow, it's negative I plus j plus k. That's interesting. So this is not going to be 0. All right, so the curl of f is not going to be 0. Now, what does that mean? Okay, let's go back to our summary. Okay, so if the curl of f is not going to be 0, then this is not a conservative. Okay, so we can see that we can conclude that f is not conservative. Okay, otherwise the curl of f must be 0. Okay, f is not conservative. Okay, this vector field is not conservative. Yeah, it's not conservative. So with summary says that if it's conservative, then right, then the curl of f must be 0. Okay. So the divergence, right? The divergence of f is 0. So then f might be, I can again, might be the curl of some vector g, okay? Vector field g, might be. Why? Because that's not a sufficient necessary condition. Okay, we go back to here. If f is a curl of g, then divergence 0. But conversely, it's not necessarily true, right? Yes. All right. So now let's prove that. Okay. And in fact, and f is going to be the curl of g, and I can give you the formula. It's going to be y squared plus z squared, and x squared plus z squared, and x squared plus y squared. Okay, you can check that this is indeed it's coming from g, but it's not always true. Okay, this is so special. That's the way I constructed the F. Okay, it's coming from and come from some G. But in general, it's almost impossible to find the G. Okay, if the divergence of F is 0, it's harder to find such a G. Okay, there's no standard way to do that. All right, so we stop here and we continue our lesson on this in the next class.